Hey everybody, John Wagnon here with Dev Central. We're coming to you with another Lightboard lesson. And today we're going to talk about a couple of different vulnerabilities that have been hot and have affected lots and lots of people. They are Spectre and Meltdown. These are interesting vulnerabilities because they're not really dependent upon software, but they're actually targeted at hardware, like the actual processor of your computer. And the first one we'll talk about is the Spectre. So Spectre, I'm going to write it up here, S-P-E-C-T-R-E. I looked up the definition for Spectre. It's like a ghost or like this really scary thing that like no one can control. And actually the reason that this thing is named Spectre is, frankly, there's not a lot of great mitigation actions to be able to handle this thing. So it's going to be around for a while. But nonetheless, even though it's going to be around for a while, we still need to understand kind of what it's doing and how it works. All right. I would say that the entirety of the Spectre vulnerability lies in the fact that a modern processor wants to execute instructions as fast and efficiently as possible. So because of that, sometimes when you have memory and processor and all that going on, the memory that is required to let the processor know, hey, here's the results of an instruction, that kind of thing, the memory may be tied up, and then the processor, instead of waiting on the memory to be available, it's going to go ahead and execute even more instructions. So let's just say, for example, you have an instruction, x plus 1 equals y, and then the next one maybe, y plus 2 equals, z or something like that. Well, if x plus 1 equals y, if y is not able to be calculated just yet because you're waiting on a memory address space, then what the processor may do is what's called speculative instructions or speculative execution, where it'll say, hey, I'm going to guess the value of y because I think I know what it might be, and I'm going to go ahead and execute this instruction also. So when it does that, there's a couple of different terms to keep in mind as well, and they are discard, so discard and commit, C-O-M-M-I-T. Okay, so discard, that's not a good D. All right, discard and commit. What happens is, if a processor is, say, executing this instruction right here, x plus 1 equals y, and the memory space that would take up the value for y, or that would hold the value for y, if that's being held by some other process right now, and it's not available yet, and then it goes ahead and speculates the value for y and it executes this, then what's going to happen is once the memory space that holds the value for y, once that's available, then the processor will now come back and say, was this speculative execution correct or not? And if it was correct, then it will commit that value for z into memory. If it was not correct, then it will discard that, and then it will execute the correct instruction based on the correct value for y. So that's what this speculative execution does. The reason that that's a really cool thing is that speeds up the processor speed like crazy huge. And so everyone loves that. They're like, hey, my processor's all totally fast now. It's like 10 times fast. So the way that Spectre works is you have this bad guy that comes into the equation and he says, all right, I'm going to throw some values in with some very detailed or some very targeted instructions that I know that the processor is going to execute. And I'm going to send it certain instructions, and then when it speculatively executes those, then I'm going to have this covert channel that is listening to that, and it's going to effectively leak the memory of this computer out to the bad guy. All right, so to kind of break it down, just a really quick thing. Let's say that you have a set of instructions like this. Let's say you have an if statement. If x is less than, I'm going to say array, can go ahead and do this next instruction. But then what the attacker does is they send in a malicious value x into this, and it's actually greater than array 1, and because they're bad guys and they're like, hey, we're going to throw a curveball at you. Well, what the processor is going to do is it's going to speculatively execute this instruction still, but it's going to use the value that it was given for X, and even though X is now greater than, this malicious value X is greater than array 1, it's still going to kick this instruction off right here, and it's going to put that malicious value X into this array, and it's going to set that into memory, and the malicious guy, the attacker, is going to be waiting for that to happen and is going to be looking at that memory space, and as soon as that memory space gets allocated and gets used up, then it's going to know, hey, this has executed into the bad guy value for X space, and it's going to have that's basically going to create a covert channel back to allow them to see the contents of the memory, all right? Now, what's going to end up happening is the processor back here is going to figure out later that, hey, that was a bad value for X, and I need to discard that, but at that point it's too late. The memory's already been leaked, and the bad guy has the memory. So effectively what can happen is you can read the memory of the machine. This actually is a problem for processors today, and I'll put Intel, I'll put AMD, and then I'll put ARM. The bad guy can trick the processor into doing instructions out of order, then the processor will actually execute the instructions on the protected memory space, and before it can realize, hey, I just processed these instructions on protected memory, I need to not do that, I need to go back, then again, it's too late, and then that protected memory can be dumped. So the physical memory, I'll put all the physical memory can be completely accessed on this computer. All right, the reason that this is called Meltdown is because you have this idea of all of the memory on the computer, some of it's user and then some of it's protected, and there's supposed to be these effectively these walls, these guards between these two different types of memory, and because of this problem, then these walls have been melted down, and so now there's no distinction between user, like common user, and protected memory. Impact and the actions, which by the way, there are some software patches that can be run to help with this. I won't say that they're completely effective, but they're better than nothing. So if you have a software patch, whether you're Windows or Mac OS or Linux or whatever,